We'll start the lecture this morning, and really, again, we appreciate Professor Heinz Pritsch come all the way from Germany to give this lecture. You know, these opportunities are rare and not easy. I want you guys to really appreciate it. And hey, thank you. And, make best use of your time, of course, his time. Okay, he runs the show now for the next 5 days.
All right, thank you very much. So good morning, everyone. Welcome to this course. This is unexpected to get the praise before I delivered anything, but I'll take it. Okay. Good. So we have a tight schedule in this course. You see the title of the course, Combustion Theory and Applications in CFD. I have given the same course here 2 years ago. And it was just called Combustion Theory. And Professor Law asked me, and I gave the same course also last year at Tsinghua University. Professor Law asked me, could you also focus a little more on CFD, on applications? And you'll see we have one chapter applications at the end, last chapter in this course. But I think last time or 2 years ago, I didn't get really to talk very much about this. And so he asked me, could you put more CFD in the course? And I sent him a list. I said, this is what I do, and this is what I do on the first day and second day and everything. Just tell me where you think I should take something out. Maybe some things are not so important, and then I can add something. And so he wrote me an email back. He said, I looked at this now for 2 hours, and I don't know what to take out. And so I tried to add material, maybe little CFD, but I just added slides, and I had too many already last time. So we'll see. We'll see how we get through this. And hopefully I did add a little more to the applied CFD area. So I want to start out with a question. I want to encourage you guys to participate, not just listen, but also participate. I want you to ask questions once in a while, and I want you to just shoot answers at me. They might be wrong sometimes. That's okay. Okay, everyone can be wrong. I'm wrong sometimes, but we need to keep moving. Okay, so just try your best in helping me out. Okay, we want to talk about combustion. First question here is, you could take methane as a fuel, and you could convert it to CO2 and water. And you could do that in a flame, with what we call combustion. But you could also do this, take a solid oxide fuel cell. You could also convert it to CO2 and water there. You could take hydrogen, any fuel cell runs on hydrogen also, or let's say the PEM fuel cell, for example, or you could burn it in a flame. Now there are several differences, and so I'm asking what's the difference. I'm after one particular difference that makes combustion special and also complicated. So, any thoughts on this? Heat release, exactly. So the heat release is one of the most important things. You have a chemical reaction that produces heat. That's okay. But because of that, it raises the temperature. That's okay also. But now everyone here knows probably that most chemical reactions, they get faster when the temperature increases. Okay? So this means that if you have a reaction that proceeds at some speed, let's say, and it increases the temperature just by rolling off, and it makes itself faster because of this, you get a feedback, a nonlinear feedback. It just, like when I go to the speaker now, you hear this beeping sound, same thing. Nonlinear feedback. So this is one thing that makes combustion very, very complicated, because it's very, very nonlinear. Okay, you have this exponential temperature dependence, and we'll see it's not just exponential; it's even worse than that. So the heat release, that's the most important thing. Combustion is self-accelerating and therefore very nonlinear. One thing that's important, that if you look at fluid mechanics, you all have taken a fluid mechanics course at some point. you have the Navier-Stokes equations. The Navier-Stokes equations, they basically, for simple problem, let's say, they have a certain time scale. So you have a convection time scale, you have a diffusion or a viscous time scale, and so on. And if you compare these to each other, or let's say if you make the equations non-dimensional, you get non-dimensional groups. Okay? So any time you have a physical process that's just by itself, it's very simple. Very, very simple. Everything's good. Once you have two physical processes that compete somehow against each other, you will find a non-dimensional group that describes this competition. Now, in fluid mechanics, Navier-Stokes equations, you have the competition between the nonlinear advection and the viscosity or diffusion, whatever you want to call it. Okay, so the non-dimensional group that compares these two is what? This is the Reynolds number. Everyone knows the Reynolds number. So now imagine you have also chemistry going on. Then what you get is the chemistry itself also has a certain time scale. So the chemistry adds a time scale. So you can compare now the chemical time scale with a flow time scale somehow. And it could be either one. It could be the advective time scale, or it could be the diffusive time scale. Then you form non-dimensional groups. And these non-dimensional groups, we'll talk about these later. The Damm-Köhler number is one comparison like this. The Karlovitz number is just a different comparison of a chemical and a flow timescale, more related to turbulence in that case. What's interesting, though, is that in chemistry, you have many, many individual reactions. Take combustion of diesel fuel. You have thousands of different reactions that happen. And now each single reaction has its own time scale. Some reactions are fast, some reactions are slow. Each reaction has a time scale, which means you don't add, by doing combustion, you don't add just one non-dimensional group. You add thousands of non-dimensional groups. There are thousands of Damm-Köhler numbers, one for each reaction. Okay? Now, one thing we know, we'll see later on, of all these 1,000 reactions, there are only a few that are really important. Only a few that really determine what's going on, and so you don't add so many. But it is important to keep that in mind. For example, combustion that itself could be relatively fast, but pollutant formation typically is slow. Okay? That gives you two timescales already. So these are the things we need to keep in mind. Self-accelerating, nonlinear, many, many different timescales that we add. We have an interaction of the flow and the chemistry, and that's what makes a flame, and that's what makes combustion a little complicated. Now, in combustion, very often we distinguish between two different modes of combustion or regimes of combustion, whatever you call it. This is premixed and non-premixed, okay? And probably everyone knows this, but it is very, very different. The physics that happen are very, very different. So premixed is you have a fuel and air, you mix it together, maybe you spark it somewhere, and then you get a flame front that just burns through this mixture. Example here would be spark ignition engines is an example here. You see these are the valves. This is an internal combustion engine from the bottom through the piston, basically. You look at the valves here, and then you have ignition, and you see a little flame kernel here, and that grows and grows and just burns through the premixed charge. And another example here would be stationary gas turbine, for example. And then the other one here is that is non-premixed combustion, where you inject the fuel, maybe in liquid form or gaseous form, but you inject the fuel into an oxidizer, maybe air or oxygen or whatever, and then it can burn only when it mixes, because the fuel itself doesn't burn, the air itself doesn't burn. And so you have a mixing process going on, and you have chemistry done at the same time. A typical example here is an aircraft engine shown here, where you have the liquid fuel is the green stuff here. Liquid fuel comes in, evaporates, mixes here with the air, and then burns. And well, the reason why you have this here in the spark ignition engine, premixed combustion, you have the heat release very fast, And that gives good efficiency in a spark ignition engine, if you remember your thermodynamics course. Non-premix combustion is very stable. It's very hard to blow out, and for an aircraft engine, as you might imagine, that's an important feature. I want to show you how this looks like. Unfortunately, I forgot to bring a cigarette lighter. Anyone has a cigarette lighter or matches? Yeah. Good. So, brought this thing here, which got me stuck in the airport. I said, "What is this?" On the screen they have, and see this thing here, just in black. And they said, "What is this?" And I said, "I think it's an umbrella." I said, "This is not an umbrella." So this I didn't bring. This I got somebody to get this for me here. Okay, good. I want to show you how a flame looks like. Okay, so what do we have here? This is we should extinguish this. So I have this tape here, and I forgot to bring fresh tape. Maybe I use my fingers, but then it gets awfully hot. So if I fall down and die, you should do something. Okay, you see, the nozzle is cold. It takes a while to start burning. So now I do this. I close these holes here. Now you have just fuel here, propane, coming out of this nozzle. The propane itself can't burn. It needs to mix with the air. As I said earlier, the mixing it's quite slow, the mixing. This laminar here also. So mixing is very slow. But while it mixes, it starts burning. And you see, this is a lazy kind of flame. This is what you have in your fireplace at home, or you have a wood fire, campfire, whatever. This is what you have. You have the fuel and the oxidizer separated. And it's kind of a lazy thing. Interesting, though, is, and we'll talk about this a little more later, interesting is that if you look at this, it has the fuel just on the inside, but the fuel is cold, okay, because it comes out of the bottle. It has air outside. Air is also cold. So it's really hot only in a very thin layer in between these. So you could actually stick your finger here inside, and you wouldn't burn, well, let's say the tip of your finger. You wouldn't burn the tip of your finger, okay? The rest of the finger would burn, but the tip of the finger would not burn, okay? So now, if I let air in, then if I open one of these, you see I'm covering some air holes down here with my fingers. If I open one of these holes, then you get some air coming in, maybe not enough at this point to burn all the fuel, and we get something that is partially pre-mixed now, okay? So you see the yellow color goes away, it gets more blue, and what is that? No, I think it's okay. I think it's okay. Good, or should we turn the light down? What's that? Oh, the blue. Yeah, okay, turn the light down. So, now it's all pre-mixed. You suck the air in here, it mixes with the fuel, and then, so if you could turn this off here, then I could hold it here in front of the blackboard. And then you see stuff coming out. First of all, you see this is not lazy anymore. This is a very vigorous flame, and it accomplishes all the heat release in a very, very small distance here. Okay? I mean, of course, turn it off. Of course, you also have, here in this case now, you also have the air that mixes in. So the total velocity that you have coming out is much higher, it's turbulent, it mixes very fast, and you get a lot of heat release. You can turn it up again. So, demonstration here is just, you do premixed, you do non-premixed, it's very, very different. That's all I want to show you. Exactly what we're looking at, we'll talk about later. Thanks for the lighter, by the way. Get one of these cigarette lighters and look at it. One thing that's very interesting, I'll focus again on this later on. You look at it, you have the same thing. It's cold in the inside, it's pure fuel. It's cold on the outside, it's pure air. It's hot only in a thin region in between where fuel and oxygen are just in the right amounts. And then what you have is a very thin flame. And you should look at this flame. You see it in blue. You see a very thin blue layer. That's what you have. In a car engine, for example, you have this blue layer. Now, in a car engine, the temperature is very, very high. Okay, which means the higher the temperature, the thinner this layer, sorry, not the temperature, the pressure is very, very high. The higher the pressure, the thinner these layers become even. Okay, so combustion, all the music that's going on in combustion, it plays in a very, very thin region. You see a big flame, you know, from a wood flame or whatever. All the action is in very, very small volume in very thin sheets. Okay, typically. All right. You stay here. I want to see you here every morning. Good. So that's just to, you know, set the stage for what we want to look at. I want to go through these slides here quickly. You have seen these many times. Our age now is really determined by the use for energy. There's nothing more important right now in this world than thinking about how can we get our energy safely. 20 years ago, the question was just how can we drill out more energy from under the ground or whatever. Today, we're thinking, at least 90% of the people, I think of global warming and all that, and know this will be disastrous, and we need to think about how to do this better. So, now, pollution, outside of just thinking of CO2, of course, is still an important issue, and sometimes this is forgotten these days a little bit. These you have seen. This is an old graphic here from the 2011, what does it say here, International Energy Outlook, but things haven't changed very much. What you see here is that the total demand for energy here increases from 2008 to 2035 by 50%. This is a lot. You see here that OECD countries, they don't change very much. It's mostly non-OECD countries, which is here that are responsible for this. This is basically India and China. This is not to say that people there are bad. It's just that OECD countries, we use so much energy already that you don't need to increase this even more. And here there's a demand is coming up in the next years. And so oil here is the dominating source of energy. And transport, traffic and transport accounts for about 25%. You see, this here is the world energy consumption, projected world energy consumption. You see liquids here. This is oil, basically, coal, natural gas, renewables, nuclear. Renewable is wind, water, solar, and all of this. And so this is the exact same data. So this is just absolute numbers. This here is in percent. And you see that the amount of liquids goes down, or demand for liquids goes a little down. Coal stays roughly the same. Coal is particularly bad in terms of CO2, as you know. Natural gas stays about the same. Renewables, and that's important, will increase a little bit. But not very much. Let's say it's a factor of 2 or so in the next 30 years. But a factor of 2 is not very much. It's not going to change how things are done. You see, you have to add, these are all fossil fuels. You have to add these up, and then if you take renewables and nuclear here together, you end up at about 20% of the total share in 2035. And maybe the new reports, they're a little different, but that's the basic message. Nuclear here is even before Fukushima, so this might even be less at the end of the day. Okay, so the message of this is we will need more energy. That energy will be supplied by burning fossil fuels. Okay, and now we can see, does that have anything to do with CO2? If we think about, or with global warming, Greenhouse gases, there are different greenhouse gases. You see here nitrous oxide, most of all methane, carbon dioxide. You can convert them all back to CO2 equivalent, and combustion is, and CO2 is responsible for about 85% of all the greenhouse gas emissions, okay? So basically greenhouse gas emissions are CO2, mostly CO2. Where does the CO2 come from? There are different sources how we generate CO2 in the world. 95% of all of this is combustion. So combustion is responsible for 80% of all the greenhouse gas emissions. And the expected increase in CO2 emissions is 43% again in this time span. So we project, you see, because we use a little more coal here, or a lot more coal actually in that time. And again, coal is particularly bad. Okay, so what can we do about this? There are different things. Maybe hydrogen economy, no CO2. CO2 sequestration, here carbon capture and storage. That's another alternative. Question is always, you can think about how to collect the CO2 from combustion, but then the question is, where do you put it? You need to dig it up in somebody's backyard, and that's an issue. Biofuels are another interesting alternative. Biofuels, the real problem is there's not enough land to grow biofuels. But what's very interesting about biofuels is that you can have even a negative CO2 balance. I mean, you can if you grow biofuels, you burn them and you combine it with carbon capture and storage. You have no net CO2 emissions. You just take CO2 out of the environment. Okay, so these are things that one could think about. The point is there will not be a silver bullet. There's not one thing that does everything, that solves the whole problem. But there might be many little things. Okay, if you have one technology, maybe let's say biofuels, that replaces 5% of the energy demand, and you have 20 of these, then everything's good. Okay, you have 5% maybe solar, 5% wind, 5% water, whatever. Add all these up, and maybe you get to 100% at some point. So, well, increasing efficiency, that's one important one. Increasing efficiency is something that, of course, here combustion theory can help you with, and that's the point I wanted to make here. Increasing efficiency is not easy. You take a combustion device and you want to increase efficiency. You will see that there are other aspects that you have to consider. Typically, if you want to design a combustion process, let's say a gas turbine or whatever you want, there are always three and a half, let's say, or 3 + 1, things that you have to keep in mind, just from the technological side or from the combustion side: efficiency, emissions, and stability. Okay? So, for example, take a stationary gas turbine. Stationary gas turbine typically operated premixed, lean. Okay? If you go very, very lean, you reduce emissions, you reduce NOx, but the process becomes prone to instabilities. Okay? Or, for example, take an aircraft engine, is very stable. Again, as non-premixed, you have a lot of emissions. Let's say comparably, if you want to go more premixed, then you reduce emissions, but you lose stability. And the same thing can be said about efficiency, where you can trade off efficiency here again for stability. For example, HCCI engines, promise high efficiency, low emissions, but it's hard to design a really stable combustion process and so on. So, but there are many new technologies. People say sometimes, combustion, there's an old research field, but that's true. I mean, really, the combustion research started millions of years back, but, with the Stone Age people trying to rub stones against each other, and it didn't work, and then they took sticks, and then it worked or something, I don't know. But Started a long time back, but still, every single day, you hear people come out with new technologies. And the problem is sometimes our understanding that we have right now, it's not made for these new technologies. We need to learn something new. And here, just a list of examples. Aircraft engines, I mentioned this, have very stable, but have a lot of emissions. And so here's a new concept that NASA's working on. Lean direct injection, you try to make things, there's a simulation of this, you try to make things more pre-mixed, and again, that comes with issues with stability. You have liquid fuel, but still pre-mixed and so on, so it's kind of a mixed combustion mode. In the automotive sector, people talk about HCCI, people talk about homogeneous charge compression ignition. In Europe, people talk more about so-called downsizing. You try to make the engines smaller and run them always at high load, which gives you better efficiency for a typical engine. It's not throttled, then you good efficiency, but the problem then, there are knock issues, so-called super knock, where you get one knock event maybe every 10,000 miles, but that one event, it will destroy the engine. So you can imagine this is very, very hard even to look at this experimentally and so on. So that's another good example for how theory can really help. Electricity generation here, oxy-combustion, where you try to burn with pure oxygen instead of with air. What's the advantage? If you burn carbon, let's say, with pure oxygen, you get pure CO2, or you take coal, you get pure CO2 and water, you condense the water out, you have pure CO2. You can dig it up in your neighbor's backyard. So that's the oxy combustion is for sequestration or carbon capture and storage. IGCC, flameless oxidation here is another interesting technology where you burn at relatively low temperature. You don't get a flame even. You get more distributed combustion mode, but almost no. You don't see a flame even. You don't get any emissions with this. Or not any emissions, but has potential to get very low emissions of NOx and CO also, and so on. So the point I want to make here, all of these, they might be outside of the typical combustion ranges. They're all very, very different, maybe from that simple flame I just showed you. And what this means is we need to develop new theories and so on, and develop a new understanding. And here numerical simulation can, of course, help to design new combustion technologies in concert with experiments, of course. But if you want to do simulations of something you don't understand, that is a problem. And so the new challenges in the field of combustion, they also prompt us to develop new simulation technologies and also new theory and models. Okay, good. So that was just a short introduction. We will. So the aim of this course is that I don't want to give you. You'll see that we'll do. Talk a lot about analysis, and some analysis we talk about here was really done maybe in the 30s of last century. It's really old. Does that still help us in any way? Yes, we'll see some things are right, some things are wrong. But at the end of the day, what I want is not recipes for you to, you take 1 kilogram of fuel and then I give you a recipe and you tell me then how it burns. I want you to get a deep understanding of combustion. I want you to, at the end of this course, maybe 1 week is too short, I want you to feel, in your stomach, how all of this works, okay? So that's what we're trying to do. Some of this stuff, as also Professor Law pointed out, is theoretical, and lots of equations and stuff, but the course is called combustion theory after all, so there's at least no false advertising. But again, I mean, it should this is how you should look at it. Don't look at it as I need to be able to redo this derivation. No. sometime when you look at this, you should think, oh, this, derivation, maybe here I should use a similar trick or whatever, Good, so fundamentals here, thermodynamics, we'll talk about thermodynamics, kinetics, we will not talk about kinetics, because there's a parallel course, or in the afternoon, there's a course taught by Professor Green, and he will talk about kinetics, so we'll skip that part here. Also homogeneous systems, we'll skip that here because he will, explosion limits and all these things, he will probably talk about it. Fluid mechanics, heat and mass transfer, we'll talk about turbulence here, for example, and so on. And applications here, all applications you could imagine. Technical systems, it could be just flames, but here internal combustion engine, gas turbine, stationary gas turbine, aircraft engines, furnaces, all of this. Okay, so really this course was developed from these notes here, combustion theory by Professor Peters. He taught this course here 6 years ago, and in large part this follows his course. It's a little different from what from the Professor Peters course, but there is this book here, which you can find online. I think it must be here on the Princeton website somewhere. Has a lot of, it's just written text, and if you are interested, this might be interesting to look at. We will, I subdivided this into two parts here, one fundamentals and laminar flames, and then part 2 is turbulent combustion. Part 1, we'll talk about some fundamentals. You've seen this many times, and I will try to go through this quickly. Then we'll talk about thermodynamics. First law will tell us something about flame temperature. Second law of thermodynamics will tell us something about equilibrium. There's a whole chapter here on governing equations. We'll skip that entirely. You have it in your handouts. If you have a need to, understand this a little better, look at your handouts. I think the one thing that is sometimes a little confusing in the governing equations or important to see is the energy equation. The energy equation, as you know, you can write it in 25 different forms, especially when you have chemical reactions going on. And so you're getting your energy equation straight. That might be a good thing to do, but everything else, I think, should be straightforward. We'll talk about laminar flames. There are two sections here on laminar premixed flames. One is just on the kinematics of flame fronts. We'll introduce concept of a burning velocity, talk about that for a little bit. And then the second part here, we'll talk about flame structure, and we'll talk about classical asymptotic analysis for understanding flame structure, and also more modern asymptotic analysis. And we'll talk not so much about the actual analysis, how to do the math, even though that's also in your handouts, so you can, in part, you can follow this. But we'll talk about the results that come out of this. There's some results that are very, very interesting. And then we'll have a section here on laminar diffusion flames. So then in the second part, we'll talk about turbulent combustion. So there's an introduction here to turbulence for those of you who haven't taken a turbulence course yet. It's very short. Actually, I teach a turbulence course also as a whole semester. So I'll try to do this here in 1 hour or whatever. Let's see how that goes. And then we'll talk about the physics of premixed combustion. We talk about the physics a little bit here about non-premixed combustion, and then there's one section here on modeling both of these. First premixed and then non-premixed, and then application at the end. But I try to have some applications also on the way. Okay, good. One more thing. Everyone knows World Cup's going on. Who's interested in the soccer World Cup? Who's not interested? Okay. Americans. How many Americans do we have here? This was bad last night. What was this? 5th minute in overtime. This was for beating Portugal. That's is not bad. Almost made it. Any Portuguese here? No, we had a conference last week in Germany, and we had 2 people from Portugal there. And we watched the game Germany-Portugal. We watched that together. It was bad for the Portuguese, but there was a lot of beer also. So here's a problem. Many of you know what I'm talking about. Anyone from Ghana here? No. The soccer game on Thursday, Germany-US, overlaps with this course. I waited with that until Professor Law left the room. So, with that would be a good idea, actually. So we need to come up with a solution for that. I think the class will end at 12:15. The game starts at noon. So we need to leave this room by 11:45. I'm planning to go to some sports bar here. Whoever wants to join me is welcome to join. Any Germans here? Okay, so you guys, my suggestion, so there are two suggestions. So we need to come up with half an hour lecture time. That could be either we start early in the morning, twice, maybe 15 minutes, that's one. Or, maybe easier, we have two 15-minute breaks. We could reduce that to 10 minutes and then, do this a few times and we should have our half hour together.
That sounds better.
That's better, 10 minutes break.
Yeah.
So we have two breaks.
Or we could stay 15 minutes longer, the last session for today.
If you stay longer, 15 minutes, I was thinking about that. That's good also. But if you stay longer, then you might not get to lunch in time and so on.
Do you want me recording the conversation?
That's whatever. No secrets here, no secrets. Don't tell Professor Law, though, that we do these things. He wants these things to be... he will watch us. Ed, sorry. This will be on YouTube. The past courses, I have 5 followers or something from last year. My daughter, she's one. She watched 2 minutes or whatever. She said I should tell you, those of you who watch it now, not you, click the like button. That's what you need to do. Okay, we should get serious again. So that's what we'll do. Reduce the break to 10 minutes. We do this on 3 days, and we should be good. Okay? We do it on 3.5 days. We save 5 minutes. This is for Professor Law. Okay, that we get a bonus 5 minutes, whatever. Okay, good. So let's start. Fundamentals. The final state, if you wait for a very long time, you mix fuel and air, you wait for a very long time, the final state is covered by the classical laws of thermodynamics. What does that mean? You will reach equilibrium. You have fuel and air, and they will react at some point. Okay? Take, for example, take this thing here. It's made of wood. This here is air. This, as you know, everyone knows, this wood and this air, they want to burn. Okay? But they don't. Now, I can show you. I could show you. If I heat the temperature up here to higher than a certain point, we'll see what that point is, then it will be self-accelerating, exothermic, it will keep itself alive. Again, I mean, this is just the signature of the nonlinearity. Once I extinguish it, it will not burn. Okay, that's just this strong nonlinearity. Okay, so it doesn't burn. Why doesn't it burn?
Reactions are too slow.
The reactions are too slow. Now we're talking about two very, very fundamental things in combustion. They're very related, but they're different. One is thermodynamics. Thermodynamics tells you where does the system want to go. If you leave this thing here for 10 trillion years or whatever, for a very, very long time, it will be mostly CO2 and water, okay, together with the air. You guys, you wait for 10 trillion years, you will not be here anymore, believe it or not. You will be CO2 and water or whatever. The equilibrium concentration is at that state. I don't know what the temperature is. It depends on the temperature. But there will be equilibrium. Everything goes towards equilibrium. We will all be in equilibrium at some point, okay, with the whole universe. Everything will be, equilibrium. So that's one. That's where things want to go, okay? You can make them go there faster, but you cannot make them, without, putting in extra work. That's what second law of thermodynamics tells you. It doesn't go the other way, okay? It's just like, if I hold this now and let it go, it will go down. If I put it down there, it will not jump on the table. Okay? Everything will go to equilibrium. So that's one. That's thermodynamics. Thermodynamics tells you what that is, that equilibrium. And the second part is kinetics. Kinetics tells you how fast it will go there. Kinetics tells you exactly how it will go there. It will tell you, thermodynamics will tell you wood plus air, at the end of the day, it will be, let's say, CO2 and water. Kinetics will tell you will have one O2. It will react with a carbon to form a CO, and the CO will do this and that, okay? So we need to distinguish between kinetics is how fast something goes, and the thermodynamics is where it wants to go. Where it wants to go is totally independent of kinetics. When we are all in equilibrium, nobody cares about how we got there. We'll just be there, okay? So that's important. We talk about thermodynamics, so that's the first thing we want to do is where do things go? We'll need some definitions here, concentration, thermodynamic variables, and so on. And then also we'll talk about mass and energy balances. So let's see. So this here is this chart. You'll see all over your handouts, your script here. You always see here, so it's part one. I put these in so that you always know kind of where we are, where we're going, and so on. So this is how you understand it. Part one. We are right now in the section fundamentals and mass balances. Okay? And in this section, we have several subsections, and this is where we are now. Okay? So next one, we'll talk about this, and then we'll go to the next section. Okay? So this is just for your orientation a little bit in this course. So we'll talk about some of the definitions. We'll talk about what is the difference between elementary and global reactions. Again, we don't talk much about kinetics, but we will talk about kinetics a little bit, especially when we talk about laminar premixed flame or flame structure. Then we talk about this, coupling functions. This is the most important thing I'll tell you today. Stoichiometry, mixture fraction. These are just basically definitions again. Okay. So chemical reactions, mass is conserved. Mass doesn't change over chemical reactions. Elements are conserved. Okay? If you have a methane, you have one carbon. You burn it to CO2 and water, you still have one carbon. In typical combustion, you don't generate elements or you don't consume elements. That's very important. We should keep that in mind. Combustion, typically we talk about mixtures of usually gases. We talk about mixtures because if you want two things to react, they have to be somehow together. I mean, you can also have surface reactions and so on. But here we typically talk about mixtures, and we talk about gas mixtures. So, think back about your first thermodynamics course. You talk about many things, internal energy and enthalpy and all these things. And in this first thermodynamics course, you talk about it for a single component system. One of the big differences here, we always have many species, mixtures, so that makes things a little more complicated in terms of notation, but not in terms of thinking about it too much. I mean, still the same laws of thermodynamics apply. So one of the things we always need to do is we need to know how much of each gas we have in our gas mixture, and for that we often use the mole fraction here. So the definition of the mole number is just the number of moles. You divide the number of moles of one particular species by the total number of moles of all species, then you get the so-called mole fraction, okay? And I guess everyone knows these things. It's just for repeating this. You can convert mass to mole number here by the molecular weight of a particular species. You can also define a fraction in terms of the mass. So you take the mass in a mixture, you take the mass of one species divided by the total mass, you get the mass fraction. Okay? And of course, you can convert mass fraction to mole fraction. Using mass or mole fraction, you can compute the mixture molecular weight or the mean molecular weight of a mixture, and so on. Now, already one should ask the question, why can't we stick with one? Why, I mean, this is all complicated because you'll see everything will always be molar and mass-based, and why can't we stick with just one of these, you know, just to keep life easy? Think about it. We will come back to that question later on. So another thing that's very useful here in combustion, you might not have looked at this in your thermodynamics course, is element mass fractions. Element mass fractions are the mass fraction of an element, as the name suggests. So take a mixture of methane and air. You can have a mass fraction of methane in that mixture, but you can also look at what's the mass of just all the carbon atoms you have compared to the total mass, or what's the mass of all the H atoms compared to the total. Okay? So it's relatively simple to do that. And the reason why it's very useful is elements are conserved. So you know the methane will be converted to CO2, but the carbon just stays the carbon. So conserved quantities are always very good in combustion research. So the way to build these element mass fractions is use this matrix here. The matrix Aij just tells you how many atoms of element I do you have in species J? No. How many atoms of element J you have in species I? Okay. So methane Aij would be you have 1 carbon and you have 4 H. It's very simple. And then you have the mass here of an individual component. With this, I converted in the number, the mole number or the number of molecules. And then I divide it by this number of molecules times the number of elements, of atoms per molecule. Gives me then a total number of molecules. With this molecular weight of the element, I convert it back to a mass, and this then gives you the total mass. And then you sum this over all species, and that gives you the total mass. So this is trivial relation here. And then I divide this by the total mass, and that gives me the element mass fraction. So element mass fraction then is given here in terms of mass fractions or in terms of mole fractions, and we use these once in a while. You'll see. Now, what's interesting is because of the definition, they're all based on the total, the total mole number or mass or element mass. All of these always add up to 1. If I sum up the mole fractions of all species, this sums to 1 mass fraction and element mass fractions also. So again, why do we use mole fraction, then mass fraction, and element mass fraction at the same time? Any ideas? Why don't we just say, let's just stick with mass fraction, and that will make life easier?
Do you need to generate additional equations to solve for more things?
Yes, but more precisely. Why? What's the advantage? I mean, if we use both, each one must have an advantage. What's the advantage of mass fraction? The mass is conserved. Okay, that's very, very good. Again, in combustion, the problem is the species always disappear, they are formed. We have equations, and these equations have a chemical source term, and that chemical source term, it always makes life very, very complicated. So anything that is conserved does not have a chemical source term, that does not depend on the chemistry, that's always good. Mass is conserved, that's very, very good. Okay, so mostly, when we write conservation equations, when we write differential equations to describe a combustion process, we use mass fractions because, you know, mass is conserved, makes the equations just simpler. Also thinking about it. Why would we use mole fractions or moles? Yeah, because chemical reactions, they're always written in terms of moles, okay? one CH4 plus 2O2 goes to products. Okay, it's always written in terms of moles. And so moles are important because of chemical reactions, but when we want to balance species, mass is better. And then also, as I said, so mass fractions, they're not conserved. The total mass is conserved. The mass fraction is not conserved because you have species that are formed and species that are consumed, but the element mass fractions, they are conserved. Okay, so that's a totally conserved quantity. So this is how we use these three. There's another one. So now we have three. We have a fourth one. They all do the same thing, really. This one is called the, what do you call it here? The partial molar density, or most often it's called concentration. Concentration is just the number of moles per volume. Why is that now an important quantity? Because chemical reaction rates are given in terms of, they're usually specified in terms of concentration of species. So a reaction rate is the rate coefficient, which has the Arrhenius factor and so on, times the concentration of the products, of the reactants. Okay, so it's just this, and this would be the total concentration. The total concentration of a system is not equal to 1. It's just the total number of moles divided by the volume. It's not 1 because it doesn't have, it's not dimensionless. All of these are non-dimensional, this is not. Okay. Good, we have the density here is just the mass by the volume. We have a partial density here which comes out of the, which actually is used to define here also the mass fraction. And these can be converted into each other. So if we look at a reaction rate, then very often we use this relation here because reaction rates are written in terms of concentrations, but our equations are typically written in terms of mass fraction. So very often we write the reaction rate just in terms of this expression here. So this rho times y divided by wi is something you always see in reaction rates, and this is where it comes from. Okay, gas equation of state. Everyone knows this. We don't need to you introduce this here. In combustion, mostly the ideal gas equation of state can be used. Okay, so the equation for thermally ideal gases can be used, which is written here. Even for high pressure, in engines, is typically a good assumption once the fuel's evaporated, let's say, is a very good assumption because not just the pressure is high, also the temperature is typically high, except when you look at rockets or something like this, then you do have to think about real gas effects. But otherwise, mostly you don't. So that's one thing that makes life a little easier. Of course, I can write this for the gas equation of state. I can write this here for the partial pressure. There's this Dalton's law, which says if I have a mixture here of different gases, then each gas, for an ideal gas, each gas behaves like it was alone. That makes perfect sense in the limit of ideal gases. So this means you have in this room, you have nitrogen and oxygen mostly, okay? And so the nitrogen, just by itself, it behaves like there's no oxygen, and it's because you have the molecules bumping against the wall. There's a pressure, it exerts a pressure on the wall, and then the oxygen also has a pressure to the wall or to anything else. And these two pressures, they just add up because they're independent. You can superpose these. That's what the Dalton's law says here. So the total pressure is just the sum of all the partial pressures. And each single molecule, it takes the full space here as if it was alone. So this is why you can write here the volume. The volume can be given here, can be computed from the mole number of any particular species and its partial pressure. Okay. As an example here, this is another thing I want to show you here. There are more slides in your handouts than we talk about. Some examples, sometimes a lengthy derivation. Sometimes something I just took out because we don't have infinite time, and I just left it there. It was something we don't need later on, but I just left it there in case you want to look at it. So I try to always mark these here with something green. If it's in your handouts, it's now hard to see. But that's unfortunate. I should do something else. Maybe put a little star there. if you see something green here, it means, we'll just skip this. You can look at it by yourself if you want. Okay, so I'll just skip this. Okay, so this was a lot of definitions. Let's talk about reactions. We distinguish between elementary reactions and global reactions. This is just now, a definition of the terms. Elementary reaction describes an actual microprocess. I mentioned this earlier. When you talk about real kinetics, this is how you have in the air here, you have an oxygen and you have a nitrogen, and they might bump together, and while they do that, you might form a third species. You might form, something else. And so these are actual microprocesses that happen. They take place if a collision between two reactions take place. These can be then, you can assign reaction velocities or reaction rates or rate coefficients or something, which can you measure for this particular reaction experimentally or theoretically. That's an elementary reaction. We typically, this is an example here. This, by the way, is the most important reaction in combustion. You might as well memorize it now. You see it has radicals here. We denote the radicals with a little circle. It's not a general convention. That's just what we do, to help the students in the beginning who are new to reaction kinetics to see a little bit what the difference is. Keep in mind, there's not, other people might not understand it. It's just here to help the students a little bit. I think everyone will understand it, but anyways. Okay, so this is how we write an elementary reaction. H plus O2 goes to, with this arrow, OH plus O. Now, global reactions, on the other hand, they just tell you the general proportions in which a fuel and an oxidizer react with each other. It could be fuel and oxidizer. It could also be some intermediate step. You could have methane goes to CO first, and then CO plus oxygen goes to CO2 or something like this. Okay, it just tells you in what proportions different reactants react with each other. So it gives you ratios or amounts of a substance that react with each other, and it does not represent the chemical microprocess. So an example is 2H2 plus O2 goes to 2H2O. Okay? That's, if these are the stoichiometric proportions in which H2 reacts with O2, but it does not mean that on the micro scale, two hydrogen molecules and one oxygen molecule, they bump together and magically just form two water molecules. What happens really is that even in combustion of hydrogen and oxygen, the most important thing that happens, again, is this reaction here. Okay? So elementary reaction, global reaction. You see the global reaction, we write this here with an equal sign to just distinguish the two and to make clear also, for you, this is a real reaction as it happens in real life, and it's just a global balance here of the amounts that would react with each other. Okay, so in a little more detail, elementary reactions observe conservation of elements. They happen due to collisions. This here is an example for bimolecular reaction. Elementary reactions also always proceed in the reverse direction. If you take a chemical mechanism, sometimes you will find in a chemical combustion mechanism that you load down from the internet or find in a publication, some reactions are explicitly, they go only in one direction, but this is only because the other direction was neglected. In real life, all reactions always go both ways. So that's sometimes here symbolized with this double arrow left and right. Now, global reactions also observe conservation of elements, of course. So that's the most important thing here, to count elements left and right and make sure I have the same on both sides. They don't take place on the atomic scale in this way. Just give a global balance. We use the equality sign. I think I said all these things. So this example here again for this reaction. One thing that works with global reactions, which does not work with elementary reactions, as I said, global reactions only give you the amount, the ratio of the amounts that react with each other. So you can multiply them with a constant. So here we have 2H2 and so on. I can divide this by 2, and I get this here, H2 plus 1/2 O2 goes to H2O. Okay? With elementary reactions, this does not work because, take this reaction here again, H plus O2 goes to this. This does not mean 2H plus 2O2 go to something, because for an elementary reaction, 2H plus 2O2 would mean that 2 hydrogen atoms, 2 oxygen molecules, they would come together in one point again and magically form these reaction products. You know, that doesn't happen. What you have is you have one hydrogen atom, one oxygen molecule. They come together, they form some activated complex, they fall apart in, you know, as an OH and an O, and that's just what happens. Okay. So this works here. I can also make this mass balances by using molecular weights. So if I have 1 hydrogen, it would be, let's say, 2 gram, equivalent to 2 gram of hydrogen, or 1 mole of hydrogen, 2 gram of hydrogen. 1/2 O2 would be 16 gram O2, and so on. So you can write this here. You can use, by using molecular weights, you can also write this in terms of mass. Okay. This, again, is just convention here for us. Nu here would be a stoichiometric coefficient in a reaction. Nu prime means it's the stoichiometric coefficient of a reactant. Prime means that of a product. Both are always positive. Okay? These are always larger than 0, but then sometimes we can also write it like this. So nu here would be nu prime minus nu prime, which just means it would be positive for a product and it would be negative for a reactant. Okay? That's if you do linear algebra, that's very helpful. Okay. Right. This is how you formulate a global reaction. My children have done this in high school, so I expect you know this. And I do oral exams in combustion, and sometimes they're not very good. The outcome is not very good. But one thing everyone always knows is how to form a global reaction. So if you don't know this, you should look at the slide later on. Okay, coupling function. I said earlier, this is the most important thing we'll do here today. Coupling functions are tremendously important in combustion. I mentioned earlier, you have, you want to describe a combustion system. A combustion system, let's say you burn diesel fuel, I said earlier, or take kerosene or whatever. Sometimes we use, when we do simulation or modeling, we want to replace that real fuel with something simpler so you can compute it. Dodecane would be a good candidate for this, maybe as a surrogate, a simple surrogate for something. Or heptane is often used as a surrogate for diesel. Heptane, a chemical mechanism, has about, let's say, 500 species or so. Then a reduced mechanism have 150. But that still gives you 150 equations. 150 equations. So what coupling functions try to do, and they're all reactive equations, what coupling functions try to do, they try to reduce this number. They try to make the number of individual equations less by coupling different species to each other. This is a trivial concept. It's really simple. It's very easy. You will see it's very easy to understand. But it's very, very powerful. Okay? So, I'll give you 1 second. Gather your thoughts. Good. Ready for coupling function. It's very simple again. So, let's say you have a reaction like this. New moles of fuel react with new moles of an oxidizer to new 3 moles of product. Okay? Or just say A plus B goes to C, but you remember the stoichiometric coefficients. Let's say this is one of these global reaction, a net reaction. Then it just means any time. So we have 3 species, which means we need 3 different equations, to describe this problem somehow. Okay? So we have 3 different equations for mass fractions. Now, mass fractions add up to 1, which means we can skip 1, and say maybe mass fraction of product is 1 minus mass fraction of fuel minus mass fraction of oxidizer. Okay? We still have 2. But now, it's interesting to realize that anytime you consume an F, you will also consume some O. Okay? In particular, if you consume new 1 moles of F, you will consume new 2 moles of O. Okay? That couples these 2 species to each other. And that's basically the general concept that the coupling functions use. So you can say, question to you is if, let's see, take a reaction, CH4 plus O2 plus 2O2 goes to CO2 plus 2H2O. Okay? Take that reaction, and now, let's say I see what I have in my box. I have, 5 moles of CH4 in my box, or 5 molecules. I have 5 CH4 molecules in my box, and I have, let's say, 10 O2 molecules in my box. The stoichiometric should work out fine. And now I let it react. And now, a certain time later, I do a measurement. I measure 3. I measure 3 methane molecules in my box. I've consumed 2. How many times has the reaction taken place? Trivial question. I shouldn't say trivial question. Nobody answers trivial questions. There's always a little danger. There's like a 1% chance that you're off. Okay. I need brave people here. You are brave already because you are in combustion science, which is one of the toughest problems, the toughest subjects, I think, in the world. So you have demonstrated you're brave already. So I have had 5. Now I measure 3. How many times has the reaction occurred? Very good. Twice. Okay? So let's say I said I had 10 O2. Okay? I had 10 O2, and now I measure 6 O2. No, it's different. Okay, I had 10, now I measure 4. How often has the reaction occurred? 3 times, okay? How did you do this? You took the change I had, dN, okay? And you divided it by the stoichiometric coefficient. Okay? I said 3. No, I said the change was 2, and you divide it by 1 is still 2. Here I said the change was 6. You divide it by 2, you get 3. Okay? Very simple. What's most interesting about this is that this ratio, delta n divided by nu, that is the same for all species. Okay? Immediately you see, in my second example, I will measure 3 CO2. You take 3 divided by 1 is 3. I will measure 6 H2O. Take 6 divided by 2 gives you 3. Of course. Okay? It makes perfect sense. That's it. That's the coupling function. Okay? We just say dN I divided by nu I, that's the same for all species in the reaction. So that's the same as dN1 by nu1. 1 could be the fuel or it could be anything else. I can write this now in terms of the mass also, here by dividing by molecular weight. Now, you will see this throughout this course. Some of these slides I updated this time because I wanted to make the slides a little more readable or better for you and better for me, and so on. So I took some of these from my German course, and then the student translated it into English. And but some of the equations they changed, but some of the equations they didn't. They forgot to change. And you see, m. Usually we use W for molecular weight. In the German course we use m for whatever reason. So m and W are both the same. They're both molecular weight. B is that would be the abbreviation of in German for fuel. Okay, so B and F also is the same. I didn't see it here. I have a note in one of the slides later on. B means fuel. Okay. Just bear with me on the little German things that you'll find in these notes. Anyway, so I can write this then also in terms of mass fraction here, and then I can integrate this, and I integrate it, let's say, from an unburned state. So you have a box, you have fuel and oxygen, and then you let it react for a certain time. So I integrate it from 0 to that time, and if I do that, I get you know, it's trivial. I get YO2 minus YO2 unburned divided by this is equal to Y fuel minus Y fuel unburned divided by this. Okay? That is the coupling function. That always allows you, if you now solve an equation only for fuel, for B, it will allow you at any time to compute oxygen mass fraction. Coupling functions are very, very powerful. You can also take now the equations. If you write an equation for this coupling function, for this, here, write an equation for the right side, the left side here minus the right side, and you'll see it has no chemical source term. So the coupling functions can be used often, especially when you have single-step reactions or things like that. Oh, I think our break was at the 1:45, right? Yeah. I thought the break is at. So we'll start as we said. We won't talk about it anymore, but we'll meet at 7 minutes past 10. Okay.